Okay, well, let's get started. So, welcome to our Wolfram Technology Conference. This is our 37th annual technology conference. I've got a lot to talk about today. We have a lot going on. I'm going to kind of give some headlines here. Other talks at the conference will go into much more depth, much more technical detail. So, well, coming soon, we have version 15, and I'll talk about some of what's going to be in that. I'll be using, of course, the latest overnight prototype build, so you can expect that it will crash at some point. It's a good way to do quality assurance. Um, this has been kind of a long journey. If if we look at kind of let's see if I can get this to do the right thing here. Um, let me see. Do we have a failure already? That's bad. Okay, well, the we're kind of uh, let's talk about kind of we have a it's been a long journey. This is kind of the picture of all the different versions, major versions of Mathematica and Wolfram Language since the beginning in 1988. Since our last conference 1 year ago, we've released version 14.2 and version 14.3. 14.3 was a particularly big release. I'll talk about what was in that as well here. We also released in the last year our notebook assistant. Um, 2 years ago, well, January of 2024, we released version 14. We're kind of on a rhythm these days of about two releases per year and a major release every 2 years. And we have our version 15 coming up very soon. Well, so um, these are definitely AI years. So there are lots of confusing and sometimes downright silly things that are being said and going on. I have to say we are in a rather lovely position with respect to all of this because as the froth subsides, the things that we have been building all these years seem to be ending up in just the right place. The things that we had planned starting 40 years ago, the kind of technology stack that we built is now ending up being positioned in sort of exactly the right place, which is wonderful. I mean, I like to think of myself as having kind of lived the AI dream now for 40 years. What do I mean by that? What do we hope for from AI? We kind of hope that we'll be able to define what we want to do, and then some machine out there will just automate doing it. That's kind of, and that story of you think of what you want to do and then something automates getting it done, that's really the story of our technology stack and of Wolfram Language over the last 4 decades. It's kind of what we've been trying to do is to give you a way so that you can control things. You then have this sort of superpower to actually achieve the things you want to achieve. So what's sort of new in the world of AI and the big story of LLMs is what one can think of as sort of providing a linguistic user interface to things. I mean, we introduced a targeted version of that in Wolfram Alpha in 2009. Now we kind of have, by being able to have kind of natural language input, small fragments of natural language input, we had a very different capability there because we were able to go from that natural language input to our full kind of precise symbolic language underneath. Now we have kind of a sort of full conversation version of that linguistic interface with LLMs, and it has some different characteristics. I mean, I have to say that, ChatGPT was a big surprise to everyone that worked at the time it did. I'd been following that technology for a long time. There was no indication to anyone that finally one would get a version that actually worked. Well, there's a great tendency when there's a surprise like that to take the one data point and extrapolate it to the moon. I mean, I feel like I understand this story pretty well in terms of what ChatGPT and LLMs can actually do and so on. Many of you may know, I right after ChatGPT came out, I got so fed up with people asking me how does it work that I wrote this little book about it. And nowadays, that book is now in it's in a dozen languages with all kinds of different funky covers and all sorts of things like that, and small sizes and uh, weird covers and all those kinds of things. Somehow it even reached the kind of airport bookstore level of of visibility. I have to say that more than 3 years after the arrival of ChatGPT, I thought that my efforts to explain it would be sort of just one in a zillion books. But I think it's the only kind of sort of high level but somewhat technical description. Um, and what is perhaps more notable is that apart from a few numbers that are in that book, what the book says is still current, despite the fact that huge amounts of investment have gone into LLMs and so on. What one had to say about what was going on and what was going on when ChatGPT was new is really very much the same story as what's going on today. It's I have to say, watching the whole kind of story of AI has been it's been interesting to see. I mean, a fun fact that some of you might not know is that my first company, which I started in 1981, and which made a thing called SMP, which is kind of a forerunner of modern Wolfram language, in which I kind of got to try out all sorts of cool ideas about computation, some of which were good, some of which were not so good. We kept the good ones and made them even better for Wolfram language. But that company started in 1981 under some pressure from its then venture capitalists. Um, by 1982, it had become an AI company and had, in fact, renamed itself to Inference Corporation. That's what it finally went public many years later. But I find it interesting that back in 1982, one was still thinking that one could have an AI company. The story of what AI was a bit different in those days. Um, I think it's worthwhile to say that there's sort of two big things one should know about neural net AI. First thing is, when's it going to work? If you have a problem where getting it sort of 80, 90% correct is what you need, then it's going to do well for you. If you're kind of ranking results in a search engine or something, and one of the top three results is what you need, fantastic. Even if one of the other results that are in the top three are total nonsense. It doesn't matter. You got what you needed. Um, but if you want something where it really is necessary to get things 100% right, don't look to neural nets to be able to do that. It's something, if you want something where you're building sort of a solid piece of technology where you're going to be able to build this tower one piece on top of the next, then that's not something you're going to get unaided from a neural net. Neural nets and things like that are really good at doing things which get sort of 90% correctness. And then you spend the next many, many years sort of trying to fill in that last 10%, and it won't work with kind of the neural net story. Second thing to really know about neural nets is that the history of it, of what's happened, is that things advance in jumps. There are, back in 2011, kind of when deep learning was young, image identification got solved, and then later on, things like image generation and speech to text and so on. And then in late 2022, kind of the generation of text is something that got solved with large language models. Things go in jumps. What new modalities of neural net AI start working, and then what happens in the years that follow is that there's sort of gradual, slow improvement, but the main advance already happened. It was a jump. And there'll be other jumps. I'm sure we'll get kind of good robotics, we'll get video generation and so on, but we won't suddenly get the jump to the perfect artificial general intelligence, whatever that might possibly mean. I have to say that I shouldn't sound jaded, but I'm reminded of some ancient story about teaching a horse to talk. It's kind of somebody had the bright idea, let me tell some king I can teach a horse to talk, and get the king to fund the project for 5 years to teach the horse to talk. Needless to say, it didn't work. Well, obviously we didn't push hard enough. We got to get more funding to try and get the horse to talk for another 5 years, and so on. And I think I feel that that's quite a bit of the story of kind of the goal of AGI. It doesn't matter that it's a nonsense concept. That's actually a good thing because you can keep going and saying we need kind of more money to get closer and closer to this goal. Now, the reality is, by the time you've raised enough money, you've got a war chest to do almost anything. And many interesting things may happen. We've kind of seen this picture before to some extent with blockchain and so on. Big war chests raised, those ones didn't turn out to work that well. I think perhaps things will work better in terms of what can be done in general with the kind of war chests that are raised on the sort of hope of going in the direction of sort of the ultimate AI and so on. You know, I have to say, talking of kind of the horse's analogy, I sort of see current AI as kind of being like a wild animal, maybe a horse, maybe something else that's been captured. And that wild animal is what it is. It does a whole bunch of things. It and maybe you can breed it to be a little bit better. But the real value from it comes in how you put harnesses on it, how you kind of connect it to machinery to get it to do useful things, whether it's a horse pulling a plow or being pulling a carriage or whatever else. What really matters is how you connect it, how you harness it, how you connect it to sort of machinery that does things. Well, in the world of kind of computation, we're in this wonderful position of having a bunch of that machinery. You know, we built this unique tower of technology around precise computation and precise knowledge, and that's a thing that you can connect this linguistic interface that's provided by modern neural net AI to. You know, I think when back around 1980, I was kind of thinking about how to deal with kind of making knowledge computable and how we could build a thing that, well, these days we call a Wolfram Alpha-like thing. And back in those days, I kind of assumed that we need sort of this brain-like AI to be able to do it. But the more that I actually understood about science and computation, the more I realized that that was not the correct core approach. Um, it's and actually in modern times, I've kind of been sort of trying to understand the foundations of what happens in machine learning, and that's an interesting story of sort of building these lumps of irreducible computation. But in any case, as a result of sort of things that I thought about science and computation back a long time ago, I realized that the real way to make the world computable is not to try and build a brain like AI, but instead one gets vastly more leverage by building a kind of formal structure on which one can make this sort of whole tower of capability. Now, I think sort of the story of a lot of intellectual development is a story of increasing formalization from things like logic and antiquity and mathematics. Those are the things that let one sort of define things precisely and build sort of arbitrarily tall towers of capability. And in the 21st century, sort of the great formalism, the great paradigm that we have is computation. And the way I see what we've been doing all these years is to build kind of a language that allows one to formalize expressing things computationally. Back maybe 500 years ago or so now, mathematics made a transition from just talking about things in terms of words to having a systematic formalization with mathematical notation and all those kinds of things. I see our effort with Wolfram Language and with our technology as doing that for computation. And I think the what we saw with mathematics back 500 years ago was being able to make sort of mathematics systematic is what led to the development of algebra and then calculus and then all the mathematical sciences. What I see our mission as being is to make computational things similarly systematic, and from that to allow the creation of kind of a computational X for all possible fields X. And I think it's fair to say that sort of 4 decades into this enterprise, it's working really well. We have a kind of a a language in which one can think about things computationally, a language which kind of makes this bridge between what we think about and what we can actually computationally implement. I have to say, a big motivation for me to go to all this effort to build all this stuff so I could use it myself. And particularly in recent years, I'm excited that that's been able to lead to some rather spectacular science. Maybe I'll mention that at the end if I have a chance. But it's even more fulfilling, perhaps, than that, is seeing so many other people be able to use what we built and achieve so many great things. And it's always fun for me to discover that across just a vast range of fields, the intellectual leaders of those fields rather uniformly use our technology and often have been doing that for decades. Well, I think we've done something big. I know that many of you understand that. It's always difficult to communicate big things. Um, and the eventually the big things become like, well, there was this historic thing that happened. But in the moment or the decade, it's much more of a sort of frustrating story of why don't people understand this? So we've been trying to make an effort, and I think this will be a theme of ours for the next few years, of trying to explain what we're doing in better and better and more broadly. So, for example, one thing that we did recently was to make a new homepage for our company. Let me bring that up. And so trying to explain what it is that we've been doing all these years, I think it's fair to say that we have been delivering the computational future since 1988. And if we go down through this, we'll talk about what our beginnings with Mathematica and kind of the fact that that idea of unified approach to computation is a thing that we have now been able to apply across all kinds of different areas. We're now looking at a few of the areas to which we have seen it applied, and each one of these areas eventually we will be providing lots and lots of information about the use of our technology in these areas. Well, lots of people, I'm so happy to say, have been using our technology, discovering many things, inventing many things. Our goal is to deliver tools for the world's intellectual leaders across lots and lots of different areas. And this is kind of a story of what our core technology is about. And needless to say, unlike those kinds of web pages where the web page doesn't even say what the company actually makes, we actually want to show off some of our technology. Right here, you can see a few examples of Wolfram Language at work. And then we're talking about the deployment of our technology in all of these different areas. And then it's on to, hey, you should use this yourself. Or we could help you build things with all of this technology. Well, how how can people get into our technology? This is one of the kind of long time challenges. And the um, um, one of the things that is sort of a new game in town there is the notebook assistant. So this is something we introduced at the end of last year, and you can bring it up. And the idea is the thing that is great about it, it's something that is built on top of kind of the linguistic user interface provided by LLMs. There's lots of technology that is kind of computational technology that is kind of harnessed, used as a harness for that linguistic interface. But you can ask all kinds of things. Let's see what I could ask here. Let's see. All right, let's ask. This is a funky question, but the idea is to say something very vague and then have the notebook assistant try and take, oops, try and take that kind of vague thing that you've said and try and see whether you can go from that vagueness to sort of an island of solid computational capability. And okay, now it's finally ready to roll here. So I asked something crazy here, and it's all right. It's you never know what the LLM is going to start it off doing. I think that's unpromising. I don't think it's going to be able to actually solve it. Let's see if I say okay, that's not good, is it? Well, I told you I was using a prototype of things. You know what? I'm going to ask, how could I map a horse sound onto a human one? See how it does with a question like that. And then we'll tell it, it's a very vague question, but let's see if it can give us some idea about that. So it's making various suggestions. And okay, now here's the important thing. It's actually giving us some code here, which we can go ahead and copy, and we can probably run this code. Sometimes the code will just nail it and give us exactly what we want. I don't know whether that okay, so it's got a thing here where it thinks it's generating a horse sound. Let's see whether that works. No, that didn't work. Well, let's see whether at least a piece of this worked. And um, the that's interesting. Um, but the main point is that this gives you sort of a direction to start going and actual functions to start using. It's a pity that that particular thing didn't work so well, but it's showing me that I could use audio pitch shift and pitch recognize and so on, and then try to shift. It's kind of a good idea that it has here. Um, let's see. Let's just see what happens if I were to say, I'm really surprised that didn't work. Let's just see whether I just say horse. Um, and let's say I want it's um let's see what happens if I do that. Okay, well, let me not spend too much time on this, but I wonder what that is. That's a sound entity. Um, and maybe I can just say audio of that, see what that does. Um, no, okay. Well, all right. So the LLM didn't quite, the notebook assistant didn't quite nail giving me something that I could immediately run, but at least pointed me in a direction and gave me some ideas about what I could do to approach this crazy problem. Well, it's uh, I think one of the things I was mentioning is kind of building harnesses uh, to put around LLMs to have them be able to be as useful as possible. Something we've been working on recently, we'll be bringing this out in the next short while, is a collection of technologies that uh, I that are around what we call computational augmented generation. So there are really three things that we're doing here. I've kind of got a summary of them here. The first is an MCP service, a Model Context Protocol service. Kind of the idea there is if you've got a system that is making use of LLMs, you've got some kind of chat bot, you've got some kind of code assisting system, you've got something else that is kind of a general system that's using LLM technology, then this new, somewhat standard MCP is available that lets you plug tools into that system. So what we're providing is an MCP service that lets one plug in Wolfram Language, Wolfram Technology. It's actually a combination of Wolfram Alpha and Wolfram Language. Plug in Wolfram Technology into other LLM AI tools using MCP and provides those tools with the material they need to make good use of our technology. So that's the first thing. That's if you've got an existing consumer product and you want to plug Wolfram technology into it, as a consumer, you use the MCP service. Second thing we're providing is what we call Agent One, which is an API that is kind of it's a kind of all-in-one solution that is both an LLM with its linguistic interface and so on, together with full kind of Wolfram technology to be able to do the computation side of what you want to have done. The third thing that we're providing is our component APIs. These are all the pieces of our computational augmented generation system that can be accessed separately for people who are building large scale systems, for example, building large scale LLM based models and so on. And the idea of computational augmented generation is essentially this sort of an idea that's become quite popular is retrieval augmented generation, where you take whatever the question you that was originally provided or the prompt that was originally provided, and you say, of some corpus of text, another material that I have, what fragments of that were closest to, in some semantic distance sense, were closest to the um, the thing that was asked, and then you surface a bunch of those close results, feed those as a sort of enhanced prompt to the LLM, and have it start to do computation. For us, instead of doing retrieval against a fixed corpus of material, we're able to do arbitrary computation. So that initial kind of question that gets asked, we then can compute from it, and we uh, and provide kind of prompting for an LLM. In the end, it'll be a back and forth process in which, in the end, we're doing the heavy lifting of the computation, and the LLM is providing the linguistic interface to kind of give the sort of smooth conversational result at the end. Well, as an example of all this, let me see if I can pull up an example of Agent One. So this is uh, the Agent One API plugged into a thing called LibreChat, which is just a simple um, um, chat interface. And let's see what I might uh, do here. I might uh, let's say, well, let's just do something. How about I ask a question? When does log x get smaller in magnitude? I wonder, you probably type this question than square root of x. You'd probably type that question directly into Wolfram Alpha, but let's see what happens. Oh, great. Well, that's always a bad sign. Okay, let's see if this worked. Something went wrong. Never a good sign. Let's see if I have something. Let's see if I have uh, okay, here's a question I asked yesterday. Just what earthquakes have there been recently near Hawaii? So what happened there was Agent One went out and used our CAG APIs to ask some questions of Wolfram Alpha and Wolfram Language, gave a bunch of results, and then the LLM kind of packaged that up to give a smooth kind of linguistic result as output. Here, for example, oh great. Well, it should have had a plot there. All right, we're seeing very leading edge stuff here, so that's what we get. Well, okay. So I mean, we can try, maybe we can try something else. Does this? I think this is just not going to work. Oh well. Um, all right. So it's uh I have to say, in the whole effort of using of seeing what's happening with kind of modern AI and so on, we've been using machine learning and one might call it AI methods within our company for lots of things for decades. I mean, there are two main ways that we've ended up using that kind of technology. One is for cases where there are no right answers, where you're sort of trying to pick something which kind of looks as good as possible, but there really isn't a right answer, for making heuristics for those kinds of things. And the other is in cases where there are guesses where you can operate by making a guess for what the answer is, and then there's a way of solidly checking that answer. So, for example, questions about, and one example, the first of these is sort of what algorithm should you use? Well, you can try different things. They're all the algorithms will work, but some may be faster than others. There's the one thing actually that we have coming in version 15 is some quite LLM-like technology that's being used to kind of have heuristic guesses for even things like symbolic computations, where we can readily check the answer, but we're having that guess, having that thing that is almost like human intuition, guessing the direction to go, is a very useful leg up, and is something that we can then sort of confirm by doing actual precise computation. There are all sorts of applications of kind of this whole idea of kind of all these AI ideas. In the past, we've had kind of statistics on numbers. Now we have kind of textistics on text. Sometimes it's just a matter of extracting structured data from texts. Sometimes it's a matter of sort of inventing ways to operate directly on text and kind of maintain these kind of uh, things which are sort of concepts that we can now operate with as a thing that is actually something we can compute with. Another thing which I personally have found rather useful in modern times is what one might call thematic searching with LLMs. So, for example, I've been interested in whether there are funky things that have been discovered in the history of experimental physics that might be relevant to various kinds of models that I've developed. And but I nobody's going to have written down with the same way of describing things that I have what happened in some unexpected experiment that was done 50 years ago. So what one has to do is to make sort of a thematic search of the scientific literature for those kinds of things. And that's a place where LLMs seem to be very useful. Can one expect the LLM to just do the science? Well, no. I mean, ultimately, the doing of science, sort of the serious doing of science, is kind of a tower of things going on. That's a story of kind of irreducible computation, where the things that neural nets do are just, they are sort of a shallow form of computation, a shallow but broad form of computation. What you ultimately need to sort of make serious progress in working things out in science is to do sort of many steps of irreducible computation. Well, there are things that one can absolutely do with that sort of seem to kind of magically make progress in science. Very confusingly, one might think of some of those things as AI-like things. It's very confusing, not least because AI, as it's now being thought about, is doing very human-like things, and the things that one can do that are sort of magic ways to make progress in science are very non-human kinds of things. I mean, the thing that for me has been a particularly big direction is what I tend to call ruleology, the study of kind of what's out there in the computational universe. And let's see if we can uh, do something with that here. The kind of the idea is to just go out into the computational universe and and see what's out there, and what is often out there are very, very surprising things. So here I just poked out into the computational universe some of my favorite cellular automata. We can be pretty certain that none of these particular images have ever been seen before. Whether they are sort of new, fresh scientific phenomena, and the question then is, can they be connected to things that are relevant to things that we are trying to study? But being able to sort of go out into the computational universe and find things that have never been found before, that's a very easy thing to do. The real challenge is to connect those things that we want to have done. So, talking of kind of searching the computational universe, I have to say I often do very big computations, and personally, I have I think it's now about 240 cores that I just have as sort of my home computer, so to speak. So I get to use parallel map and things like that. Back in 2008, we introduced parallel computation in Wolfram Language, and parallel map allows one to take kind of a computation that can be run across many machines and immediately run it in parallel. But what if I want to go even bigger than my 240 cores? Well, there's a new product that we have coming out very soon that is intended to provide sort of instant scaling for Wolfram language computations. And let's see, sorry, we uh, we call it Wolfram Compute Services. And the idea is that you can just say something like um, you could just say something like remote batch submit. You do a computation. Let's do just 2 plus 2. You do it as a computation just on your own computer or your own cluster of computers, or you can say remote batch submit of that exact same computation, and it will be sent off to a compute service provider in the cloud. We take care of sort of all the details of how that works. You'll get this remote batch job object. You'll get some email telling you that this job is starting. Eventually, you should get email telling you that it is finished. I think it'll look something like this. Um, there's the email you get when it starts. Then you get email to say it's finished. And then you get this is the remote batch job object. This is the evaluation result. You just use that piece of code in any Wolfram language session, and you retrieve the results of this computation. So this is a good way to do very large, to immediately be able to scale up, to do sort of arbitrarily large, 1,000 core, multi-thousand core, multi-hour computations. And this is something that we'll be bringing out soon, Wolfram Compute Services. It's a good thing if you don't have your own supercomputer. If you happen to have your own supercomputer, something we'll be bringing out later is what we call HPC kit, which is a kit for allowing you to set things up so that you can do remote batch submit on your computations to your own supercomputer cluster. Well, okay, let's come back to sort of local Wolfram language. Talking of kind of going big, one big theme this year, starting in version 14.2, is tabular. And tabular is a way of dealing with large-scale tabular data. So, for example, I could take a data set of all the trees in New York City. It's like an 80 megabyte data set. I can just read it in here. It all happens very efficiently. I could also be doing the same operations I'm about to do on this data set maintained remotely in a file or in a remote database or whatever else. But here we now have this whole notion of a tabular, and a tabular, there are many operations that can be done on tabular. So for example, I could say that a tabular is typically a thing which we can think of in terms of our technology as a list of associations or an association of associations. It's a thing where there are many columns of data. So you can take, for example, we call this NY trees. You can say the tree underscore DBH column, just make a histogram of of the values from that column of data in this tabular object. And that just works there. That's a general thing one can do with tabulars and also now with data sets is to reference different columns for different operations, whether visualization or otherwise. We could ask as a new thing coming in version 15, the tabular structure. No, actually, this part exists in 14.3. This is kind of the underlying structure of that tabular, all sort of rather efficiently stored and so on. Here's another tabular. This one is about penguins. And what you can do, all sorts of operations, like you can sort this by the body mass column, or you could say you can construct new columns from the penguins data set from species and flipper length. This is now a new tabular with 2 columns that just does that. You can now do all sorts of things. You can say construct columns where you're using some function operating on the data in the existing tabular. Here's the result. You could, for example, aggregate some rows and make a new tabular summary of those rows. Something that is new in version 15 is the ability to have all sorts of formatting in tabulars. Actually, you'll notice that there is a new construct. We're always adding these new kind of convenient constructs to the language. This is the cyclic construct, which is what allows you to get these kind of sequences of colors in the tabular. Cyclic is a general construct, so if I make a table, I can make a cyclic list with from sort of minus 10 to 10. This is how you would do that. Well, here's a summary. This is now a tabular summary of this is a new thing in version 15. This is a sort of a the beginnings of kind of generic data data analysis for an arbitrary tabula, including very large ones. This is kind of a summary about penguins from that particular tabula. Um, let's see. Um, let's see. Another big thing that's coming in version 15 is a lot stronger time series. We are kind of using our tabular technology as a way to an integrating time series with tabular. So a time series could have this is a time series about a hike, and each time mark, each time point has a whole array of different properties that are stored as columns in this tabula. Now, just like for any other tabula, we could take this, we could just make a list line plot of this tabula for different columns in that tabula, so there we'll get that result. Now operating over a time series here, or we could do the same thing from taking the tabular and finding geopositions and then making a plot of geopositions from this tabular. So the main thing is much stronger, more efficient, more capable time series. We're dealing both with time series and event series. Time series where you're kind of filling in values, where you're assuming that it's a continuous thing that has a value at every time. An event series where it's like this happened and then another thing happened and another thing happened. There's kind of a somewhat different calculus for dealing with time series and with the event series. All of these things with tabular work both in memory, local files, remote storage, databases, and so on. There's well, let's see. There's all sorts of, let's see what I have here. Um, these are other examples of, oh yes, let me show you this. This is a so here I've got a tabula, and I'm saying take those two columns from the tabula and plot weight column against the MPG column. Okay, here's a new thing that first part of which we added in version 14.3. This is the function list fit plot. So we're saying, okay, I've got this data, but I want to get some kind of local fit through that data. That's we can now immediately do that by using list fit plot. We can tell list fit plot that we want it to be an exponential fit, and we want to plot various kinds of bands for that fit. So now you're sort of immediately getting that fit added to your data. In version 15, there's also the notion of model fit, which is now allowing you to get a symbolic representation of the model that was fitted to that data. And in this particular case, it's sort of choosing the best model. It chose a polynomial fit to that data. We could ask it to make an exponential fit to that data, and we can then extract properties of that model. It's a very lovely symbolic way of representing kind of models for data and so on. It's something where we've had sort of junior versions of this for probably 30 years. This is now the definitive version that's really convenient to use. Another thing that's coming is handling categorical data. Again, something we've been able to do in some forms for a long time, but this is now kind of the full industrial strength version of categorical data and all the sort of calculi around dealing with discrete categorical data. So, for example, there's both nominal data where it's like heads or tails, neither one is any sort of better than the other, and ordinal data where there's a sequence that can be defined from, let's say, none to very light to etc. Once you have ordinal data, all sorts of operations like sorting can work on that ordinal data. So here we sorted this using the fact that this is an ordinal scale. Well, okay, so that's a little bit of things that are coming computationally. Something big that came user interface wise in um, um, in the my gosh, what am I not seeing here? Oh yes, there we go. That came in version 14.3 is dark mode. So you can press this button and say, show my notebook in what on earth? Help. That is no fun. Why? Humph. Okay, I'm going to do something here. Let's take that notebook and let's um let me just do something here. Um I am hoping that I can take this and move it here and then go here and switch to dark mode. There we go. Something went wrong with the prototype build. Okay, so this is dark mode, now supported, now very broadly supported. It's rather non-trivial to you might think, oh, it's easy to make dark mode, but it's not. Um, you have to kind of rethink sort of everything, not only about user interface, but also about computational kinds of things. Like the colors of those curves have to be ones that will work both in light mode and dark mode and so on. So uh, now, oops, okay, hold on. Let me try and rearrange something here because I want to show you some lovely dark mode stuff, and somehow I have been blown up by this build that is not working. So let me just uh, do this. See if I can recover this here. If I'm lucky, I can make this work here. Okay, here we go. So that's kind of a generic red disk, but we've also introduced, partly for dark mode purposes, partly to just make graphics look better all around, this notion of standard red. Red is just the raw RGB 100. Standard red is a red that is chosen to look good, both in light mode and in dark mode. And so for lots of colors, there's this notion of a standard version of that color. So we put a bit of quite a bit of effort into kind of uh, oh, this is not now the latest version to sort of spiffing up lots of colors of things, both for light mode and for dark mode, and getting colors, getting good default colors that will work well in light mode and dark mode. There are all sorts of new constructs, like the notion of a light dark switched color that will be have one form in light mode and another form in dark mode. All right, I'm going to go back to this latest version here. And now um, show you some other kinds of things. Well, yeah, in something that is coming in version 15 is this notion of a theme color. These are colors that are part of the user interface, and they're things that can be from the system or from style sheets and so on. You can get access to them programmatically that allows you to create interfaces and so on that will work in light mode and dark mode and in different environments. Well, in let's go here. We can something we did. This is in version 14.3. Is geographics got updated to be more beautiful and to also work well in dark mode. And it's okay. We can take this, for example, and we're also using vector graphics for more and more things for geographics. Another thing that is new is the ability to have, when we have something like a feature space plot or something of that kind, there's a question where there are a bunch of labels that are included. This is a very bad sign. This is what I get for running a prototype build. The idea is to be able to, no, that didn't do anything. Um, the idea is that when you have some kind of plot that um, has kind of a choice of uh, how much um, how many labels, for example, to fill in. This is a way of being able to specify um, uh, what um, what density of labels to fill in. Um, that's um, let me just show you that. Hold on. Just for the sake of being able to illustrate this. Just show you that here. Kind of the idea is this notion of a labeling target, which kind of tells you how hard to push to put labels, in this case for flags. If I said labeling target dense, then I would get something where it's going to fill in a lot more um, uh, a lot more flags as labels, and you have control over how that works. Okay, so um, there are all sorts of new um, capabilities that are coming. Um, let me show you uh, things like circular histograms and all sorts of fun things like that. But let me show you something else which I think is important. Let's hope it works. Here's just a list of plots. I just made a table, a 3 by 3 table of plots. Okay, what if you wanted to combine these so that, for example, their axes got combined? Well, if you just want to combine them as a sort of visually, you can use graphics grid, and this will make a collection of those plots that have been combined, but the axes will still be separate. There won't be any attempt to kind of combine the axes. Coming new in version 15 is the notion not of graphics grid, but a plot grid. And, well, that was anticlimactic. Okay, sorry, let me just, I know what's wrong. I'm not running the right version here because I was running that. Okay, let me show you here. Um, the idea of plot grid is to um, be able to actually take those plots and combine the axes across plots. So one way to think about this, as we design kind of our symbolic graphics capabilities, there are kind of outside in ways to do things and there are inside out ways to do things. So for example, for each of these plots, I could have said from within the plot, I could have said axes goes to this or that. That's kind of an outside in way to do things. Um, and the uh, uh, the um, the way that this is kind of a different approach. This is a sorry, that what I just said, if you specify the axes, it's kind of an inside to out way of doing things. This is an outside to in. So you've got this whole graphic, this whole plot, and you want to take all those plots and from the outside put them together and combine their axes. I think this is a super useful thing. I've certainly wanted this a zillion times. It's very awkward to do this particular operation from the inside out. Now we have kind of the outside in version of this as well. So uh, let's see, other things. Well, in version 14.2, actually, we oh, I should mention another thing, which is in making kind of graphics now, we added a couple of versions ago, we added things like haloing as an effect for dealing with curves. We're using haloing now when you put a fit on top of a plot, it's going to use haloing to be able to distinguish that kind of the fit curve from the things that are behind. It's a very lovely thing made possible by the kind of this underlying capability for things like haloing and graphics that we've been able to do. Well, okay, let's dive into some math kinds of things. Something we introduced in the most recent version is a array expand that's operating on matrix power there. We can go ahead and let's take something like this. We can say component expand of an inverse of this thing that is a matrix symbol and a cross product. We now get the components from these matrices and so on. We could also say we also now have the notion of non-commutative expand. This is operating on dot product. We also, with much more effort of computational capability, we have non-commutative Groban basis and in general simplification for non-commutative kinds of operations. And in the next version, we have that for Clifford algebras, Grassmann algebras, Weil algebras, all those kinds of things. Very useful for doing well, areas of physics which have been formalized using non-commutative variables and so on. Finally, we're able to make all of that stuff computable in an efficient way. All right, a very different direction that we're going in version 15 is symbolic music. So this is a music note, and we can, for example, make a musical score with a collection of music notes. It's going to look more beautiful when it's finished here. We can take something like a musical scale and we can make, oh, I don't think that was some, we can do something like, well, okay, this is just a musical score. We can now say, I don't know if this will work, but we can make a musical transposition of that score. That wasn't very exciting because it just moved the notes by some semitones. We couldn't really tell what happened there. But this isn't quite finished yet, but for the next version, we'll finally be able to do what sort of Pythagoras thought one should be able to do, sort of make music computable, so to speak. Very different area. Let's talk about chemistry. Chemistry is something that we've done a lot of work on in recent years. Kind of the idea is molecules are a thing you can compute with. And sort of molecules and atoms are as definite kinds of things in our universe as numbers. Let's be able to compute with them. And we're able to now do an awful lot computing with molecules. So something that we could just take that particular molecule, make a 3D plot of it. Something that is new, coming in version 15, that is not a good sign, is being able to do electronic structure computations on molecules. And let's see if this works, even though it looks pink here. This is now hopefully going to plot. There we go. There are some electron orbitals plotted for that molecule, and everything here is computable. So it's a we do these computations. We can get an object that we can be dealing with computational geometry and all those kinds of things. Also for biomolecules and so on, we now have local protein folding capabilities for getting approximate protein foldings and so on. Well, there's always more math to do. And so in version 15, for example, we're adding new functions, zeta functions, various kinds of polylogs, harmonic number functions, all sorts of things like that. We're now able to compute a thing like this in terms of multiple zeta functions and so on. This is these are kinds of things. We've got Hilbert transforms, Lommel functions, all sorts of things, kind of filling out what is possible to do in math. It's a lot of work to make all these things happen. I've been an enthusiast to polylogs, for example, for nearly 50 years. We finally have managed to make efficiently computable lots of types of things with polylogs that were never computable before. Well, in lots of things we do, things are sort of always more complicated than you can possibly imagine. Here's something with geoprojections, where this is a new capability for doing, let's see if this works, various new ways of computing geoprojections. You can guess that geoprojection was kind of hard to compute and to add all those grid lines to, and to take sort of this representation of the world and correctly transform it. Now all that stuff just works. Um, Not only sort of here on Earth, so to speak, but we've also added a lot of capabilities for astronomy. Uh, that's super boring. I guess that star is not up right now. I'm sure if we do this for the sun, it is daytime where I am. So yes, it will actually be able to show astrographics for the sun. Something else, the computation of eclipses. This is now working out uh, when is the next eclipse going to take place in New York City. We can ask for a map of that eclipse. These are all sorts of difficult computations that we're now able to do. We're also able to compute things about orbital elements. Something coming soon is orbit computations for satellites and other kinds of things. Um, the Okay, it has to download the ephemeris to work out the orbital elements for that asteroid and so on. Um, well, all right. Another direction is things about geometry. Let's make a region here, a geometric region. Here's a geometric region. We can now do things like make a compute the mean curvature on that surface, and in this case, make a plot, a surface density plot showing the curvature on the surface plotted over that surface. Or we could take something like a we could take data on a moon of Mars. Here's Phobos. There it is. And we can do things like we could say, highlight a region that is the shortest curve between a bunch of random points. So what we're doing here is we're finding geodesics shortest curves on the surface of Phobos and plotting them on that surface. Well, okay, another different direction is PDEs. We've been building up for many years now, a couple of decades actually, building up our capabilities for doing computations with partial differential equations for physical systems and other things. And first, the big challenge was doing the geometry necessary to do those computations. The second big challenge was kind of just setting up the models of things. So, for example, this is what we need to set up a computation in magnetostatics. We've introduced things like magnetostatic PDE component and magnetic potential condition. These are sort of the raw materials that we need to be able to do computations with set up with physical systems. So in this case, we now computed, we solved the differential equation corresponding to this magnetic field. Now we can make a stream plot. That's the magnetic field around this funny shaped object. Okay, so there's an awful lot that one can do with uh, with PDEs. We've been developing kind of a whole series of monographs associated with PDEs, explaining how one can do things. Let's say there's a Helmholtz resonator. We're kind of describing how to set that up. And then these are all click to copy pieces of code, allowing you to kind of actually build up things with PDEs to do all sorts of modeling. And it's now a very rich system, both dealing with kind of engineering style modeling and physics style modeling with for quantum mechanics, soon hopefully also general relativity and so on in the system. Well, uh, so that's something for dealing with PDEs. When we're talking about engineering systems, there also are large systems of ODEs, and we've had our system modeler product, which is a product for handling, being able to manage and solve large systems of ODEs that represent engineering systems. Here's a simple model of a car. We can take that and now compute from that. We'll say, let's make a system model plot, and now it'll do a bunch of computation. This is a representation of a system of ODEs, but it's also a representation of an engineering system. We're now going to use that representation, do a bunch of simulations, and hopefully compute all sorts of properties of this car with a battery in it. Okay, a new thing in version 14.3 is the idea of doing system model validation. So this is again a big technology stack that starts from our ability to represent system models, to have symbolic computable representations of engineering systems, and then the ability to make assertions about those engineering systems, symbolic assertions about engineering systems. That requires us to introduce a kind of temporal logic. So this says system model always, that for all times it will not be the case that it will be the case that this it will not be the case that one is sustaining a this temperature above 301 for for 10 minutes. So this is kind of a condition on this kind of system, and we're going to say, based on our model of the system, will we always satisfy that condition? And the answer, I think, in this case is no, we don't satisfy it. But we can say, well, show us how we don't satisfy it, and we'll get this kind of plot that shows us the where that wasn't satisfied. Well, and we can probably even plot for the original. What is this going to do? Oh, this is just plotting that temperature as a function of time and seeing that the condition, the symbolic condition we've given, was not satisfied. Okay, also in the engineering direction, talking about control systems, here's a simple model for a simple control system representing a helicopter. So here's a particular way of filling in those numbers. This is kind of standard control theory way of looking at a pole zero plot. We can now try and make a controller for this engineering system, an LQ regulator. This will try and make a controller which will keep this system in control, so to speak. So we've now built kind of the sort of full stack that one needs for doing these kinds of control problems, sort of all within Wolfram Language. Well, let's see. Going on, another area which is something that has been very powerful in Wolfram Language for many years, is things with graphs. Many new things coming to graphs. This is a new kind of graph layout, planar orthogonal layout for graphs. The another thing that's coming, let's see if this is going to show something I was mentioning earlier. This is using haloing as a way, actually it's not so exciting in this particular case, but showing sort of overlap of one thing in the graph with another. Okay, another capability that is coming is editable graphs. So this should make a graph that if I click in the right way, yes, if I click in the right way, I can edit this graph and move nodes around. Most of the time, it's a lot better to use automated algorithms, but if you want to, you can move that node around by hand to just sort of deal with the fact that the embedding didn't quite work the way you wanted. That is now something that is possible with editable to true for graphs in Wolfram Language. Talking of graphs, another thing that's coming is graphs with ports. So far in Wolfram Language, one's had a graph where the sort of the edges coming out of a node are all just coming out of that node. Now we can say one edge comes out on port A, another edge comes out on port B, and there's a whole elaborate calculus of what one can do with ports with graphs with ports, and we'll be introducing the beginnings of that in version 15. Well, that's sort of the early stages of a whole story of what one can call diagrammatic computation, and that is not a good sign. And I am going to do something here to make that have a higher probability of working. Okay, let's try this again. And lovely. That's okay. That's, by the way, a nice mechanism that exists to update resource functions. It doesn't stop the computation, but it allows you to make an update to go on from there. Okay, diagrammatic computation. So the idea is to represent essentially functions and generalizations of functions by diagrams. So whereas a function normally has just one output, a diagrammatic object can have many outputs, and you can start building these kind of networks of functions with many inputs and outputs. and you can kind of arrange those things here. This is kind of a way of building up sort of it's beyond functions, beyond sort of traditional functional programming. This is kind of a thing that we're starting to be able to introduce, and in many areas there has been sort of a diagrammatic calculus that's been introduced. We're trying to generalize that in a way that will work for a very wide range of purposes. So, for example, we have we built up sort of sophisticated quantum formalism in Wolfram language. Here now we can use this mechanism to take a quantum circuit operator, make that into a general diagrammatic thing. It's I might mention that so this is sort of a coming attraction is we're trying to understand how to sort of generalize functions to this kind of diagrammatic formalism. I might mention that we've done a lot with our quantum framework. Our quantum framework is built out in many different directions, very widely used in the world of quantum computing. And by the way, also plugs into some nice things with our physics project, but that's a different story. This is just more examples of kind of where one can go with diagrammatic computation. That's a lambda expression. You can, let's see if this works, to arrange that. Okay, this particular thing, it was able to arrange that lambda expression in a way that you can see how the computation works. Well, talking of language enhancements and language design, there are many sort of small changes and that are very convenient. So one thing that's been asked for a long time with is you might want to sort of nest withs. Well, now you can just do it all in one with. So multi-argument with is now available in version 15. Actually, the main challenge with multi-argument with was not the computation. It was actually being able to do syntax coloring that worked correctly in the case of a multi-argument with. Okay, a few other things I'll just mention because I think they're really useful and people don't know about them as much as they should. Several versions ago, we introduced the idea of nothing, a symbolic thing that just disappears when it appears in a list. We also introduced the notion of splice, something where you can take a sublist and have it represented by a symbolic splice object, which splices itself into a list. We also introduced the notion of threaded. So we have had listability since the very beginning. This is a way of controlling listability, of threading into the insides of a listable object. So this is threading XY into the insides of that object. Something new, I think, in 14.3 is element-wise, which is kind of an anti-threading. So element-wise takes, in this case, this is a modification of the less operation that operates element-wise on that list. So it's now taking the less of 1 and 1, 0 and 1, and so on. Okay, well, there are lots of kinds of design, that gets done. I have to say, one of the things that I have considered to be a design mistake that happened when I was not paying as much attention in 2007, when we were just about to bring out Wolfram Alpha, is the notion of having chart style and plot style be different kinds of things for charts and plots. Now in version 15, it's plot style all the way along the line. And that was a tricky thing because there are certain differences in how those work in different kinds of functions, but I think we've resolved all of those. And now we have something that's easier to understand and easier to remember, and easier for both for humans and for AIs to get right. Other kinds of things that are sort of obvious, but well, let's see. There are other things that are coming. One big thing is about error handling. We've had things like confirm and enclose as sort of symbolic ways to encapsulate errors. There's a new mechanism with throw exception, catch exception, particularly relevant for kind of large scale programs built with Wolfram language. It's a sort of safe way to handle kind of error propagation and so on. That's coming. Another thing for large program development is the structured package format. This is a way of going beyond things like begin package, end package. It's instead a way of having one be able to set up collections of packages which all communicate correctly with the right context and so on, all handled automatically. That's coming in version 15. Um, Something which came in version 14.2 or 3, I can't remember which, is modernization of percent. So percent has always been this kind of slightly ugly thing where it works fine when you're in the session, but if you leave the session, it doesn't work. Well, now when you type percent, you'll get a pull down which shows you how to have a percent that refers to a particular thing in the notebook. So this now refers to line 15 in this notebook. If I save this notebook and reopen it, this thing here will still refer to that same place in the notebook. This is a very convenient thing. I find myself all the time when I type percent, I just hit return, and that then makes it a positional percent that will always refer to the same thing. Sometimes I want actual non-positional percent because I just modified this line and I'm re-evaluating it. But often I just want to refer to that position in the notebook, and that's now possible with positional percent. There are many other kind of typing conveniences which have been added. For example, one here, if I select that and type a brace, that will add a brace in there. That's just a typing convenience. There are other kinds of things that are more conveniences. This is for videos. Videos, we've been able to manipulate videos as this is a little video here. And the point is that we can now take, we can now take that video and resize it. So that's a convenient thing. When you generate a video, you can generate a certain size, you can resize it directly within the notebook. There are also a lot of other mechanisms that just point out to people a lot of these constructs like videos. This is something that is, you have a choice. Where do you store the video? Is it in the notebook? Is it, which might make the notebook big? Is it stored in the public cloud? Is it stored in a local file? Where is it? If it's stored in a local file, if I send this notebook to somebody else, they won't have that same local file. If I store this in the notebook, they'll be able to get it. If I store it in the public cloud, they'll also be able to get it, but it won't sort of gum up the sending of this particular notebook. So those are other kinds of things. So another thing that's coming is fancier handling of interaction with external systems. So this is now showing the new version of greater than. This is starting a Python session, but it allows you to control that that Python session. And so there's all sorts of options here for what session you want to run and so on. An important thing that we introduced was the ability to encapsulate the ridiculous mess of libraries and so on that you get in languages like Python. That's what we don't have in Wolfram Language because we put in the effort to make a sort of coherent, unified, integrated design. So it isn't just people building random libraries that do random things that don't connect to each other. That's what we don't have. But if you have libraries that are set up that way, you're running Python or something like this, we now have a way to completely encapsulate all of that mess so that you can just call it from Wolfram Language just with that single sort of entry point, and it automatically gets provisioned in a Wolfram Language session. And we've done that for also for R as well as for Python. There's quite a list of options for what you can do. You know, you can run the shell and things like that in this. I don't know what happens if I do that. I think it'll. Oh, okay. Um, uh, didn't like that. But anyway, you can run lots of different external languages interactively here. You can also run them programmatically. The encapsulation of things like Python means that you can have function repository functions that are backed by things like Python code or R code. You've also are able to back them with dynamic libraries through our foreign function interface and so on. Another external interaction, kind of external interaction capability. Well, there are lots of new import-export formats. One of the notable ones is Markdown, being able to both import and export Markdown. Also various kinds of other notebook formats that are kind of knockoffs of our notebooks from 1987. You can import from those notebook formats. You won't be able to do very well exporting because they don't have all the features that we built over the last 38 years or something. But with Markdown, it's a convenient thing that you can go back and forth with Markdown for those capabilities which Markdown does support. Another thing that's coming in version 15 is WebSockets. That's a thing which has been asked for a whole variety of purposes. Now is going to be available. Another thing is the notion of GPU arrays. We introduced versions of this, but we're steadily making them better. The issue is, okay, so my machine had a GPU, so I was able to do this. That is a thing which is stored in GPU memory. And that means, and I can do a whole bunch of operations directly on the GPU. And we're setting it up so that we can specify that things are in GPU memory so that they can efficiently be manipulated there. Another big thing is incremental functions. So we introduced a version of this in version 14.3. There's a much stronger version in version 15. And the idea is that you can have, this is now an incremental function that's being compiled through the compiler. In version 15, much like we have pre-built data structures that you can use, like linked lists and so on, that you can use directly in Wolfram Language. Now also we have incremental functions that you can use. So for example, you can say, I want all the permutations of 20 elements. Well, of course, all the permutations of 20 elements, there's an awful lot of them. If you created them all at once, you would have have a big thing in memory. But instead, you can create an incremental object, which is the permutations of 20 objects, and then you can use the function next value to be successively finding the next values from this kind of mutable iterator incremental object. So that's a new thing, and it allows certain kinds of programming to be done in a very elegant and efficient way. While talking of other kinds of functions, something that we were certainly very much ahead of our time with was LLM functions in Wolfram Language, being able to use external LLMs to and treat them just like functions. So I defined an LLM that asks for the collective noun for a thing, and this is now for a leopard, it says it's a leap, and I could say for a crow, it's going to say it's something else. That's now using really putting LLMs into the language directly through this LLM function capability, a sort of symbolic way to access LLMs. Well, something we added in version 14.3 is LLM graph as a way to have a whole computation graph encoded in a mixture of Wolfram Language and LLM functions, with the LLM functions being able to be run asynchronously. This is kind of the computation graph that we defined in this particular case. We could take that computation graph and actually run it, and it'll run a bunch of different computation nodes and so on. It'll be running back and forth with an LLM, doing computations running in the LLM, and now we get the result. Talking of LLMs, we've kind of hooked up our technology to kind of all possible LLMs. So we've been doing, every week, we've been benchmarking now about 400 different LLMs, how they do writing Wolfram Language code, but also providing the plumbing underneath to hook up our system to all of these different LLMs. I will say that one of the things we learn from having run an LLM benchmark every week for the last quite a while is that, yes, LLM benchmarks are being gained more and more, but LLMs are not really fundamentally getting any better. They really are the linguistic interface that they were when ChatGPT came out. The value comes in harnessing them for different purposes and connecting them to tools, and that's where kind of our technology really comes in. By the way, you can get this if you want to play around with LLM benchmarks. You can get there's an entry in the data repository of all those LLM benchmarks. Let's see. So other things that are happening. There are, well, things to do with presenter tools. Let me not show those here. Another thing we're doing is documentation has always been a strong thing for Wolfram Language. We've been trying to make it even stronger. Our documentation is now not just for humans, but also for LLMs, and we're taking account of that in adding more documentation. Also, we've added for humans, we've added on the web new navigation capabilities for our documentation in this sidebar. All right, so that's a little bit on things that are going on within the system. I would say another big direction is cloud. We can take any one of these notebooks and we can publish it to the cloud. We've been getting further and further in kind of the in reaching parity between what can be done in a cloud notebook purely on the web and what can be done in in a desktop notebook. So this is it. It's when I it's still creating the cache that we'll use to be able to efficiently load everything. But there's that same notebook that I've been using here, but now deployed on the web. And more, for example, the graphics that we have here are more and more being rendered locally in the client side rather than being rendered on the server, making them more efficient and more and higher resolution and so on. So that's so big direction there is adding kind of closer parity of the cloud and desktop versions. Also from an underlying structure point of view, we've now got containerized versions, fully containerized versions that are coming very soon of the cloud, helping in all sorts of deployment of the cloud. So we've had our enterprise private cloud system for a number of years, where you can get a fully private, either on-premise or in a cloud provider's infrastructure version of all of our cloud capabilities. We've got we also have a variety of ways that you can serve Wolfram Language on servers. We have the enterprise private cloud, which provides a full notebook experience with APIs and so on in a private cloud. We've got application server, which is for serving APIs with all sorts of clustering capabilities and so on. We've also got coming soon the fully productized version of Wolfram Web Engine, which is a simpler kind of way of deploying Wolfram Engine at a server level. Also, in terms of capabilities, we have our standalone applications SDK. This is for making independent executables that package in Wolfram engines so that you can just have a program, an app that you can distribute that has Wolfram Engine included inside it. So let's see. We have something that with all of this technology, one of the principles we have as a company is to use the technology we've built. So something we've been doing over the last several years is implementing a new version of our ERP system, our transaction processing system. Let's see, where do I have it here? That's not that, but our transaction processing system in Wolfram Language. And over the last year, we've been rolling out more and more parts of that. So although you won't see it directly, inside everything that you interact with in about user portals and all those kinds of things, inside all those things is Wolfram Language. This is something as a practical matter you'll find if you use Wolfram Language and Mathematica through site licenses. You'll find the portal is much better, stronger, zippier. It's all of the administration capabilities are much stronger and easier to use. So that's something which has been the result of our efforts to implement our ERP system using our own technology stack. Also, uh, well, we've done a lot of uh, lots of things, lots of other infrastructure kinds of changes. We also like to interact with lots of external infrastructure. So, for example, we continue to interact with different kinds of blockchain infrastructure. This year, we added Bitcoin Cash and Litecoin to our collection of blockchains that we can interact with. Of course, in terms of deployment of our technology, a very large scale deployment of our technology is Wolfram Alpha, and Wolfram Alpha continues to advance in all sorts of ways. We have completed our containerization of Wolfram Alpha, something which is important for its deployment and particularly for private versions of Wolfram Alpha. That's a particularly important thing. It makes it more efficient and it makes it easier for us to run all sorts of foreign language versions of Wolfram Alpha and so on. We've added this year many new formulas in Wolfram Alpha. We've also used Wolfram Alpha as a giant source of training data because we can generate training data. It's not trivial to make sort of a distribution that represents what humans would do if they were using this, but we've been able to do that and make purely synthetic computational training data in very large quantities. Something else that's coming in Wolfram Alpha is Wolfram Alpha sort of specializes in getting very good understanding of short pieces of natural language. Something that's coming courtesy of LLM technology is being able to deal with larger pieces of natural language for solving things like word problems and for doing more conversational interaction with the system. Well, another thing that continues to advance is our repositories. So the function repository now has about 3,300 functions in it. There's a lot of great functions in the function repository. And thank you to many of you for contributing to the function repository. It's tremendously useful. It's also kind of a testing ground for things that we will eventually add to the core Wolfram language system. I mean, we've been put in the effort to keep the system compatible all the way from 1988. It takes work to do that. It takes really being sure that you've got the right design. And it takes really filling things out so that there's sort of full capabilities rather than just particular things that were the easy things to make work. The function repository is a great place to put in the things that are sort of easy to make work or the things that solve particular common case problems. But it's also a place to have a seed for things that will eventually do all the work to build them into the system. Well, we have a variety of other repositories. We also have the Packlet repository, thanks to people who have put in some major Packlets this year in the Packlet repository. The Packlet repository is a place where one is putting not just a single function. See, in Wolfram language, we're able to have a single function that does a lot. In lower level languages, if you want a function that deals with image processing, well, you have to define how you read in the image and you have to define all sorts of things about displaying the image and things like that, and you'll end up with a big library of stuff. In Wolfram language, you don't end up with that because we've already got those things about images as built-in features of the language. So if you want some great new operation done on images, you just have to implement that one function. Then you can put it in the function repository. But sometimes you are building up a whole world of new capabilities, and that's where Packlets come in, and you can define a whole collection of functions, maybe hundreds of functions that all sort of wrap around a particular set of ideas. And there's Packlet symbol, which allows you to sort of fish out individual functions from there. But Packlets are really about sort of clusters of functions. Sometimes some of their functions will be exposed as function repository functions, but more they're for whole clusters of things. Our data repository, we expect that there'll be a bunch of new things in the data repository, partly fueled by Tabular and the ability to deal with much larger data sets and maintain them as out-of-core kinds of things. Neural net repository is our place for introducing the very latest and greatest neural net capabilities, whether it's for protein folding or for doing all sorts of other kinds of things. This year, our demonstrations project, which is uh, something we introduced back in nearly 20 years ago now, it's now got, oh gosh, how many is it? It probably says here, 13,000 last I remember, different different demonstrations built with Wolfram Language. We expect that there'll be a lot more of these that are now possible. We now have a very streamlined way of using our repository system to represent and generate and set up demonstrations. So I encourage people who have things they've done that they would like to have available for the world or available for themselves to use to put them in the demonstration system. One thing I might say about the function repository is there's a public function repository which is curated by us, but you can deploy things to private function repository, and you can just deploy a function as a private function, a private resource function. That's very useful. Either so you can set up a sort of collection of functions for yourself, or if you're working with other people, you can deploy this kind of private to the world but public to your collection of people set of functions that everybody can have access to, and they can immediately be deployed and so on. Well, okay. Another new repository is our example repository. We are very much encouraged to contribute to this. This is collections of examples for Wolfram Language. These examples are very helpful to humans. They're also very helpful to AIs. And they're also a great way to showcase work that you've done of good use of Wolfram Language. Okay, so there are some other repositories that are coming, a themes repository, a style sheets repository, and so on. I mentioned that a big story for us is kind of explaining what we're doing, sort of outreach about to communicate to the world. Our academic innovation support team has done many webinars this year, and people who are interested in getting them to come to your university or other organization should contact them. They're webinars about AI literacy and fluency, nonlinear dynamics, quantum computing, and so on. Then there's Wolfram U. Wolfram U is a big operation at this point, providing all sorts of courses, a lot of university-like courses. One thing that's new here is our course assistant using our CAG technology. This is a sort of LLM-based support for people taking these courses, being able to ask questions and so on. The numbers of people who've been doing these courses are very impressive, very large actually compared to typical university courses and so on. One thing that's coming out soon is our micro-credentials. Oh, here's a typical example of a new course. This has become a popular kind of concept in the world, micro-credentials. We have micro-credentials, I think, first for our AI course coming out very soon. So another thing we're doing along educational lines is introducing our own textbooks. We've created a whole bunch of textbooks now. These are available both free online and in printed form. Well, increasing collection of them are in printed form. These are kind of college and beyond level textbooks. There'll be a whole bunch of these coming out as time goes by. We think they're pretty good textbooks that are really infused all the way with kind of computational thinking and the ability to take these ideas and kind of make them alive with computation with Wolfram Language. And I think they're good books to use for learning and for courses and so on. In terms of explaining what we're doing, we've kind of had this notion of core area pages. We have a bunch of new core area pages. There's going to be a lot more of this kind of explain what we're doing type material that we'll be adding as time goes on. We are um, um, we're going to be doing a lot of work kind of on different areas of application of our technology stack. We built a technology stack that is tremendously general and unified. And that means when there's a new field that doesn't exist yet, we're the best place to go to kind of build that field. But we also have a lot of extremely strong capabilities in existing fields, and we want to make use of kind of all the synergy that we have from all the different capabilities in existing fields. And that means we get to explain sort of how our technology gets used in different particular areas. And the we kind of want to. I showed this this network and that's part of our homepage now. Every one of the entries in this homepage, you can expect to see kind of material about sort of the vertical use of Wolfram language in that particular area and how the general capabilities we have can contribute to that area. Well, there's also lots of sort of horizontal stuff we're doing. Um, One thing that we're finally, I think, going to be getting traction on in the next little while is our data science platform, where kind of the idea is there's a lot of we have a lot of capabilities for data science, which kind of defining a workflow for people to ingest, analyze, present data, a very organized workflow to do that, sort of knitting together the strong capabilities that we have in Wolfram language. So another big vertical, a big sort of horizontal set of capabilities is for education. We have a new K through 12 bundle of our technology for K through 12 educators. We also have some actual new technology. We have what we call Quasio, which is something for sort of the mechanics of education. It's for dealing with testing and test banks and assessments, making use of a bunch of sort of high-tech Wolfram language capabilities, but applied to the very nuts and bolts kind of things that one does in education with assessment and so on. Well, another thing that we're doing is uh, something where we're making use of our whole stack of technology and the new capabilities of LLMs to make a serious effort at something which has been a long running kind of computers will one day be able to do this, but not quite yet, which is autonomous personalized teaching. What used to be called tutoring, although that's kind of become meaning just go ask one question at a time. This is about being able to lead somebody through a whole course to really understand a whole topic in a completely autonomous, automated way. So we've been doing that first for a particular course of Algebra 1, and we have now close to release our, it won't go under this name because we're actually spinning it off as a separate company. It will be it is our kind of system for doing sort of fully autonomous educational work, sort of leading one through this particular curriculum, and it's rather impressive and rather robust, and you can say all sorts of things to it. You can tell it you're interested in very specific things. It will try and adapt the course to the things you're interested in. It will try and lead you through. One thing that's really great is that instead of just saying, "Did you get the right answer?" it can kind of understand the working that you've applied and be able to and kind of operate from there. So you can kind of see it can also say not just you got the right answer, but it can give kind of a narrative report on how you're doing. And it's a fairly complicated technical system. I mean, people sort of say, "Oh, I'll just hook up ChatGPT and it'll be an education system." No, that doesn't work. What we've done is the actual hard work to both get the computational side of it done and the kind of harnessing of the AI to the point where we can really build a system that actually can autonomously deliver education. I have to say this is the sort of the first product in the whole history of our company where I have not been in the target market for at least the initial version of this, because the initial course is an Algebra 1 course, and that's a disgusting number of years in the past for me. But it's something we're actively testing it right now, and looking very promising that it really is going to work. As I say, it's kind of a sophisticated thing, and one of the things that's kind of the underpinning of it is a whole course authoring environment for authoring autonomous courses, for authoring AI-backed, computation-backed courses. It's sophisticated. It's got lots of different sort of things going on at a developer level, but this is something that we have now built, and we will be rolling out many different courses based on this in time to come, as well as the ability for other people to either work with us or on their own build courses in this framework. It's so this is a new direction that we have there. Well, let's see. Lots of other things going on. Lots of things in Wolfram Community. Uh, Wolfram Community is now about 40,000 people, but still very exclusive. We're now in a better position to embed notebooks cleanly in Wolfram Community. We're doing good SEO so if you write something in Wolfram Community, expect it to be widely seen. We're actually working on a new back end for the community website, which will be more streamlined in a variety of ways. We're also working on kind of a publishing layer to take the great things that people put onto community and make them really be fully published for the world as an archival kind of thing that people can make use of. Well, another important thing for us is our educational programs. In addition to Wolfram U, we have sort of direct education programs, our summer school, our summer research program for high school students, computational adventures, computer-based math, lots of different things that we're doing that are being very, very successful. You know, when you look at our summer school, for example, this is our summer school for grown-ups, which is not loading for some reason. And oh, here we go. What's happening? Okay. So you see lots of interesting projects done with Wolfram Language. It's kind of probably even more impressive at the high school level, seeing all the kinds of things that high school students can do in 2 weeks with Wolfram Language. When people say, "Oh my gosh, it's so difficult to do this or that kind of thing computationally," it's like, look at what these high school students managed to do in 2 weeks. And it's a good place to get some inspiration about what's possible to do with the technology stack that we've built, with kind of computational approach to things. Well, in addition to spreading our technology, we're always interested in we're always using our technology to build technology. We've been building this kind of recursive tower where the technology we built in the past has allowed us to build more technology. It's really a very amazing thing that we build these kind of core capabilities, then they become bricks that allow us to sort of build further and further. And as we build further and further, we can see more and more that it's possible for us to do. And that's been kind of the story of the building up of our technology stack over the last 40 years or so. One of the things that we've been doing for the last 8 years is live streaming a bunch of our software design reviews. It's kind of a very open way to build technology, sort of the most open technology way to build technology that I think anybody does. I've been sort of amazed that in the 8 years that we've been doing this, basically nobody else has maybe had the nerve to do this. I find it I think for both, we get great input when we live stream the ways that we're thinking about designing things, and I think it's helpful to be able to see how the sausage is built, so to speak. This year we've done 65 hours of design reviews that have been live streamed so far. I have to say that I myself do lots of other live streaming. So I have a variety of series of live streams. I've done about 162 hours of live streaming this year, with millions of hours watched, which is nice. It's These are different variety of different live streams that I do that have improved my ability to explain things, I think, and where I answer questions about a variety of topics. Well, you know, as a company, we do a lot of research. Some of it is very long term, some of it is shorter term. We have a whole variety of projects that have been running for decades. We have a very long range one that will probably break out this year. We're not really talking so much about it yet, but something that I think will be very important in the kind of interaction between AI and computation and what that all means, something that we've been working on for a number of years. Well, in addition to building technology and so on, I myself at least have been very interested in using the technology to do basic science. It's been going really well. One thing that's really come to life this year is our Wolfram Institute, our nonprofit independent institute. I'm happy to say we've been getting quite a lot of outside funding, which has allowed us to hire a collection of people to do basic science work. Very much, I've been sort of just as I try to define the strategy for our company and for Wolfram Language and so on, I'm trying to define the science strategy for Wolfram Institute and build basic science as we have tried to build technology over the course of all these years. Well, I I myself end up writing lots of stuff, and I've been writing. I don't know how many pages it is. Probably, I bet it's more than 1,000 pages already this year. And one of the things that we have now started doing is we have collected things I've written in the past into a variety of books. We are now starting to make individual EPUB books out of these long things that I write. So those have just started coming out, more to come soon. And there's actually a new book of collection of pieces that I've written about essentially philosophy over the last few years that will be also coming out fairly soon. And the something that I'm afraid I haven't had a chance to do much more work on is my book and course on computational thinking. I think it's very important, but I've had too much science and too much technology to build, so I haven't been able to do as much on that as I might have liked. I suppose I should give a very quick science update. It's been going so great. There are just a lot of ideas that sort of emerged in sort of the formalization of things about 100 years ago in, well, in mathematics, in physics. Formalization allowed a big jump to take place. That formalization also was what launched the idea of computation. But things got stuck, whether it was with Gödel's theorem or other kinds of things, or not really understanding this notion of computation, because who could do that 100 years ago when you couldn't actually run the computations? I've had the good fortune to live at a time when it has been possible to actually get real intuition about computation by actually running computations. And in a sense, that's the story of what I've been building all these years, is kind of a framework to let one understand with real clarity the sort of computational paradigm and make use of that paradigm as much as one can. And it's been possible to make really big progress with that. In fact, a lot of things that sort of got a certain distance 100 years ago and then kind of have been on incremental progress ever since, and people sort of gave up hoping that there would be more than incremental progress. I think we've been able to make sort of big jumps forward. And those big jumps forward have lots more to develop, but kind of it's been very exciting to see these things. It's sort of a mixture of having the right philosophy about what to do, being able to implement traditional science through Wolfram language and so on, and being able to do and get intuition about computer experiments. The combination of those things has turned out to be an incredibly powerful way to make, I would say, rather dramatic progress in basic science. We're doing a lot of things right now. In our physics project, the one of the big pushes is to build what we call infogeometry, to be able to build up geometry not from an underlying kind of Euclidean manifold-like thing, but instead from these kind of hypergraphs that we imagine are the structure of space and so on, to be able to build sort of all of geometry and calculus and so on from that. Now, in a sense, we put in all these years, both in the development of mathematics, building those things, but also in the development of the computational side of that, building those things for Wolfram language. We're at a huge advantage right now because we just built all that stuff computationally in Wolfram language. Now we have to understand kind of the conceptual underpinnings of that in this new role of infogeometry, but then we get to build up, we get to leverage all the things that we built computationally for traditional geometry and traditional calculus and so on, and do it for infogeometry. That will have, I think, it's hugely valuable for our physics project. My guess is that it will be hugely valuable for a lot of other things as well. For our physics project, we've been interested in kind of finding experimental implications, and that's a thing which is a lot of hard work and heavy lifting, but is finally, I think, getting some steam behind it. Another thing that's been surprising is kind of studying the foundations of computer science. Computer science has not been an experimental science for the most part. Rulology, the study of what's out there in the computational universe, makes computer science an experimental science. And you can do a lot of things in the foundations of computer science. We're really just getting started with that, but I think some interesting things will come even in the quite near future along those lines. It's also the case that sort of the things one's understood from being out in the computational universe doing experiments, one understands phenomena like computational irreducibility. Those phenomena are very important intuitionally for understanding what's going on in computational systems. So, for example, in understanding the foundations of machine learning, it's been, at least for me, very useful to understand that there is this computational irreducibility out there, and that what machine learning is really doing is, in a sense, taking these lumps of computational irreducibility and finding ways to fit them together to more or less achieve the training objectives that one is trying to achieve. That's kind of a picture of how machine learning works. Why does it work? Why does it fundamentally work? Well, it works because there's enough diversity in these lumps of irreducible computation to satisfy these training objectives that we put in place for machine learning. It also tells one, that picture tells one things one cannot expect to know systematically about what's going on in machine learning, or questions that's sort of not worth asking. So that's a useful thing to realize. One thing I might say is that from a conceptual point of view, there's a remarkable uniformity of the kind of approach that ends up getting taken. And it's in the end, it's all a story about computational irreducibility, kind of the power of computation manifested in computational irreducibility, interacting with situations where there are effectively observers like us who are very computationally limited. There's all this computational power underneath, but we're only sensing some kind of very coarse version of it in the things that we do with it. And one place where made a lot of progress in the last year thinking about those kinds of things is in the foundations of biology, and understanding sort of why natural selection actually works. why it's possible to actually get organisms that are fitter and fitter with these kinds of various fitness criteria. And in the end, the story is once again a competition between the power of computational irreducibility to create all those possible forms of organisms and so on, and the coarseness of the fitness functions which are applied, the sort of computational simplicity of the fitness functions which are applied to deciding what organism is successful and what's not. It's been interesting to see that one can kind of use those ideas to get sort of formalizations of sort of core concepts of medicine and so on in a way that I had not imagined one would be able to make kind of a kind of a computational foundation for a field like medicine in understanding sort of what it foundationally is and the sense in which kind of you have an adapted organism which is perturbed in some way. And sort of the problem of medicine is to find another perturbation you can apply that will kind of reverse that first perturbation. So actually, in kind of foundational theories of biology, a thing I've just been working on, which hopefully will come out next week, is again a surprise piece of progress in understanding kind of a foundational way to think about sort of a theory for biology. Well, okay. So those are a few things that I've been working on sort of at a basic science level that have been enabled by this big tower we built over the last 40 years with our technology. And I like to think that some of what we do in our kind of science efforts is sort of the race car team version of what you can do in the actual trucks we build that really can be useful to people in a broad way. And it's um, I'd like to think that the people and the world sort of deserve a better absorption of all the technology that we built. As I mentioned, intellectual leaders in lots and lots of fields have found our technology, made use of it, leveraged it to do amazing things. And, you know, it's uh, a lot of other people are kind of muddling through with kind of low-level languages and libraries of things that get hacked together and things that don't really make sense, things that they can't kind of don't form a basis for really having really being able to concentrate one's computational thinking in a clear way. And it's um, I think part of the there's a lot that you can kind of do where you think you're making progress because you're kind of muddling through things. You've got something that more or less works, and you kind of hack this other piece of code, and you do this and that and the other. And but with our technology, the thing that happens is you have to have a clear idea what you want to do. Uh, Once you know that, we're going to automate that. We're going to let you live the AI dream, so to speak. But it's going to stare back at you very quickly, saying, "This is the answer. This is the thing that the thing you thought of led to. Now, what do you want to do next?" And you don't just get to sort of muddle through things. You actually have to think about what are you going to do next? What do you actually want to do next? It's a way that you're going to be vastly more productive, but it's something where you kind of can't hide in just muddling through things. You're actually achieving things. And we'd like more and more people to be able to make use of that superpower that we put all this effort into building. So one thing we'd like to ask from people is if you use it, if you use what we built well, and I know a great many of you do, help us spread this. Help us explain to other people how to make use of this superpower for their purposes. And I think that we'd like to know how you use what we've done. If you've got a great way to use it, let us help you spread that, either telling the world it's yours or just spreading it, not telling the world it's yours. We're interested in kind of spreading the knowledge about how what we built can be, people can make the most productive use of it. I have to say that a lot of what's going on is about sort of the workflows for doing things. And I know I myself have developed lots of workflows for getting things done. When I've developed them, I've tried to make sure that those workflows can be captured in features of our technology. Um, for 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 many of you, you will have developed great workflows for doing things. We'd like to know what they are because we'd like to be able to streamline those workflows. If we take a workflow that you've been able to put together and we can streamline it, you're going to be able to use it more efficiently, and lots of other people are going to be able to take advantage of it as well. So we'd really like to hear from people who have workflows that they've developed. We'd also like to hear about workflows you'd like to have work in our technology, but where there's some awkward, rough spot where that workflow isn't flowing smoothly. We'd like to know about that, and we'd like to be able to see how to fix it. Well, so what does the future look like? I think, as I'm saying, everybody can live the AI dream, kind of automate going from ideas to reality. What skills do people really need to have do that? Not how to write low-level code, but instead how to think computationally, how to take kind of we've tried to provide the language to let people think computationally. Now it's a question of people getting to the point where they can routinely think computationally about things. It's kind of, we want not people taking CS 101 classes that are about kind of low-level programming, but CX 101 classes that are about computational X, computational thinking for everything. I think it's not so much about having computer scientists or programmers, but what one might call computationalists, people who can sort of take the computational paradigm and apply it everywhere. Kind of computationalists can kind of integrate these computational ideas, make use of our computational language, and apply it everywhere. Our job as our company is to define that language to do the automation. We've got a long way. We're kind of at this point very much on a mission to sort of implement everything, to kind of do what we can to kind of enable the computational future. It's we've been doing it now. We've been doing that now for nearly 40 years. Uh, and I feel like in many ways we're pulling further and further ahead of what people's expectations have been for what's possible. That's great. It's a little frustrating that that means that we have to put more and more effort to explaining in the now what it is that we've done. But it's really exciting to see what's been possible and what's coming ahead. And I just wanted to say thank you all for being involved in this journey. There's a lot of amazing things that are possible. There's a lot of amazing things that can be done, and uh, we thank you for being part of this community, doing these things, and enjoy the conference, which over the next few days, and I will tomorrow be doing a Q&A. So all those questions that I didn't get to answer today that you thought you wanted to ask, please ask them tomorrow and I'll try and answer them. Thank you very much, and bye for now.